Hello everyone, my name is Ben Mullen and today I present to you Team Boron's final project for Chem 3440 titled Exploring Ligand Field Effects and Covalency in Octahedral Chromium-3 Complexes. First, we got to go through a little background information. Now we all know from general chemistry that the d orbitals are degenerate for free ion and chromium-3 is no different. Now if we were to take that free ion and bring a sphere of negative charge around it, the d orbitals would all be destabilized, rising in energy. If that charge was then applied in a cubic field of octahedral symmetry, say through the addition of 6 ligands, these d orbitals would then be split into a T2G and an EG set. The EG orbitals are destabilized as they point directly along the Cartesian axes towards the ligands, and they form sigma-type interactions. The T2G orbitals then point between the axes and remain largely non-bonding unless pi effects are considered. Now the separation between the T2G and EG set is defined as 10dq or delta octahedral commonly. Electronic transitions between these d orbitals are then commonly referred to as d to d transitions. So why chromium-3? Well, for d to d transitions in chromium complexes, we are generally only concerned with electric dipole transitions. The probability that a photon is absorbed to cause a transition between the two states is proportional to the square of the transition moment integral Q. Now we can further make deductions regarding the magnitude of Q from the form of the ground and excited state wave functions broken down as shown. The most important of these for our system is the requirement for spin multiplicity not to change. Derivations are also not shown due to time constraints, but shown on the right side is a Tanabe-Sugano diagram for the D3 configuration. Importantly, these describe the interaction and energy of electronic states across varying field strengths, starting from on the left showing the free ion and on the right showing the strongest interaction. Both the x and y axis are then scaled by the Rocca parameter B, which describe interelectronic repulsion. The ground state configuration of D3 is a quartet A2G and is defined as 0 for all values of 10dq. Conveniently, we can now see our 3 spin allowed transitions which maintain that quartet spin multiplicity, and they are shown as following. Transitions thus should be sharp and very well defined, and this makes octahedral chromium-3 complexes a great model system for linking quantum mechanics and spectroscopy. So, why do we care? Well, D-to-D electronic transitions often give rise to the wonderful colors that we see in transition metal complexes, such as doped chromium-3 in aluminum oxide gives rise to the vibrant red that we see in rubies. Now, these colors are dependent on 10dq. 10dq is then dependent on the strength of the metal-ligand interaction as well as the electronic properties of the individual ligand. D-to-D transitions also allow for the calculation of the previously defined Rocca parameter B, as well as the nepheloxatic ratio beta. Beta describes the cloud expanding of the metal d electron clouds upon interaction with a ligand. Now, lower values indicate greater delocalization, leading to greater covalency in the metal-ligand bond. So, our goal: quantify 10dq, Rocca parameter B, and nepheloxatic parameter beta for a series of octahedrally coordinated chromium-3 complexes using UV-Vis. So, how are we going to do that? Well, first we're going to synthesize 6 octahedral chromium complexes, as shown. More will be discussed about the ligand in particular. Then we will be identifying 2 spin-allowed transitions. The first one of quartet A2G to the quartet T2G is defined as 10dq or delta octahedral. The second transition of quartet A2G to quartet T1G is then defined as 10dq plus 12b. Now, you might be wondering why the third one is left out. That is because it often falls into the UV region and is unresolvable. We can then calculate the Rocca parameter for the complex using the following equation, and then we can compare it to the Rocca parameter for the free ion, obtaining nepheloxatic parameter beta. For additional species that are not directly synthesized, we can use the rule of average environment to find species that we might find interesting, such as the hexachloro species. Shown here are the absorption spectra for various complexes that we synthesized, namely oxalate, acetylacetone, and urea. You'll see that the line color reflects also the color of the complex that was physically observed. The peaks for the oxalate spectrum match extremely well to literature. However, you'll see in the acetylacetone spectra that we could only resolve one peak due to a large excess of solid urea that co-crystallized along with it. Now, the 560 peak is very characteristic of the targeted complex, so we went with the assumption that the 400 peak from literature would be safe to use as well. Now, you'll notice the urea spectra is slightly shifted from traditional literature values, and that is likely because this is solution state UV-Vis rather than typical experimental, which uses solid state UV-Vis. Overall, they match literature. Now shown is the absorption spectra of chromium ethylene diamine. You'll notice that both features match extremely well. They're very well defined peaks. However, after returning 2 days later, we noticed that the solid that was previously orange had became a dark red. And we took the UV-Vis, and you'll notice that this little shouldering exists. And to classify what that could possibly be, we use the rule of average environment to find some mixed ligand species between ethylene diamine and water. And we believe that the shouldering is likely from ligand substitution with water, forming the two species shown below. We then performed a dissolution study on chromium chloride in water. Here is the T equals 0 absorption spectra shown in green. That was a beautiful green color that was observed as well. The peaks are very characteristic as well. After 48 hours, a UV-Vis spectro was taken again, and you'll notice that it is shifted. That is expected as it is characterized as the hexaaqua species rather than the dichloro tetraaqua species shown in green. You'll also notice that the absorption intensity is considerably lower for the hexaaqua compared to the tetraaqua, and you might be wondering why. It is a 20 to 30% decrease as shown here. To analyze this, we need to consider the symmetry relaxations in our complex. So in centrosymmetric complexes such as OH symmetry, DDD transitions are formally forbidden. Now, if you remember our selection rules that we talked about earlier, we had the spin and then we had the orbital selection rule. This concerns the orbital selection rule. Now, for that, we need a change in parity, G to U or U to G. Now, that all falls out the window whenever there is no center of inversion. However, in octahedral, there is a center of inversion. If we consider our two structures for the dichloro species, we can either have the trans on the left or the cis on the right. Now, the trans has a symmetry of D4H, and the cis has a symmetry of C2V. Now, you might notice that D4H is centrosymmetric, but C2V is not. So the Laporte selection rule is then relaxed. There's only a small asymmetric contribution to the ligand field from these chlorines because there's not a huge difference between water and chlorine, as we'll see later. Free ion rocket parameters are then first calculated for chromium-3 using the ab initio ligand field theory module in ORCA-6. Initially, the DEF2 TZVP basis set was used, but this showed very poor agreement to the literature. This is because the basis set lacks the information required for multi-reference CASA-CF calculations. However, there is significant improvement upon using the atomic natural orbital, or ANO sets, as they are larger and generally optimized for calculations of this type. Out of these, ANO RCC full gave the best agreement to literature. Then, using the rule of average environment with the tetraaqua and hexaaqua species, the ligand field splitting was calculated for various chromium chloride species with a special focus on hexachlorochromium highlighted above. Nicely, these transitions fall very close to their literature values. The absorbance maxima of each complex of interest are then collected into the table shown. Rocket parameter B is calculated for each and then compared to the calculated free ion rocket parameter, resulting in the nepheloxatic ratio beta. There is quite a bit of information to unpack, but perhaps it's better when this is arranged into a series. Starting off, the complexes are first arranged in order of increasing delta octahedral, commonly referred to as a spectrochemical series. First, we have our chloride, which has pi donating capabilities that destabilize the T2G non-bonding set, which results in the smallest orbital splitting, or delta octahedral. Our next 5 complexes mostly only have sigma-type properties with very little to no pi donating character. They all donate through oxygen, which is a very poor energy match with the metal orbitals due to this large electronegativity difference. Finally, on the far right, we have our strong sigma donor in ethylene diamine. Nitrogen is a much better energy match for chromium, and this results in the stabilization of the bonding EG set and subsequent destabilization of the metal-based antibonding LUMO EG. Sadly, we were not able to include a pi acceptor representative due to budget constraints. Moving on, and arranging the calculated nepheloxatic ratio in order of least to greatest, we can assess the relative covalency of the metal ligand bond for each complex. The series generally follows theory, however, ACAG would likely have similar properties due to oxalate, due to an ability to delocalize that metal electron density throughout its conjugated system. Chloride is also expected to be the most covalent compared to what is calculated due to previously discussed pi effects. So let's wrap it all up. Octahedral chromium-3 complexes elegantly demonstrate predicted orbital splitting with electronic transitions that are directly observable through spectroscopy. UV-Vis was then able to quantify this orbital splitting and relate it to interelectronic repulsion and ligand electronic character. Calculated nepheloxatic ratios also confirmed covalent character in metal ligand bonding, thoroughly describing the expansion of the d-electron cloud in forming a complex. A final side adventure also gave an additional look into the importance of thoroughly considering the symmetry environment of the system. Some potential directions for this work would be to include a trivalent molybdenum and tungsten complexes. The 4 and 5d orbitals have a greater radial extension, which through this model should, in theory, increase covalency. Although we will need to use different approaches as there are spin-orbit coupling effects that will need to be considered, but it would be fascinating nevertheless. The inclusion of a proper pi acceptor ligand is a critical next step as this project was lacking a representative. Finally, bond distances could be approximated through this very strange relationship shown, but it was left out due to time constraints. Finally, I'd like to thank Team Boron for all the support in and outside the lab, as well as Dr. Bhattacharjee for agreeing and supporting this over-the-top project. Also, special shout out to Bling Bling AC. He's always standing there and looking cool. Thank you. And here's all the sources. Yeah.